All right, now we're going to be looking at very specific points on graphs and what we can determine about our first derivative, second derivative, and original function at each of those values. So again, I'm doing my original function in red, my first derivative in blue, and my second derivative in green, just so I can kind of keep organized with information and things that I know. Okay. All right, so let's write down some stuff that we know about our graph at point A, our original function at our letter A at this point. Okay, so I know that G, and this is probably going to be a lot of writing, so I'm going to go ahead and write up here that G has a local minimum. That's one piece of information I know about this original function. So then let's talk about what that means for my first derivative. So that means that my first derivative has to equal 0 at that point, and it changes from, if I have a minimum, that means that my slopes were negative and then they went to positive. So my first derivative equals 0 and changed from negative to positive at that point. Lovely. That means that let's see, one other thing I know about my graph at this point is that G is concave up, which means that my second derivative is positive, which means that my first derivative is increasing. Well, and that makes sense too, right? Like, along with being able to talk about that your second derivative is positive and your first derivative is increasing. Well, you can't go from negative to positive without increasing as well. So G prime, it was negative, went to positive, and that is the definition of increasing. And so that would be the information that we know about this graph at this point. So these two pieces kind of go together, and then these three pieces go together. Okay, so let's do the same thing over here for letter B. So I would say that B here, that G has a local maximum, which means that my first derivative equals 0 and changes from positive to negative. I also know that G is concave down, which again results in my second derivative being negative, and therefore my first derivative being decreasing, my first derivative decreasing. And again, you can't go from positive to negative without decreasing, so hopefully that's kind of self-explanatory, but it also comes from the fact that you know that this graph is concave down, and therefore your first derivative is decreasing because your second derivative is negative. All right, let's talk about C and D. These are some very specific pieces. So at C, for example, I know a couple of different things. So my original function, how do I write this? G has we're going to call it a POI. And then up here, write a little key for ourselves. A POI. Oops. For our purposes means point of inflection. That's not jargon that's accepted on the AP test. You should write out inflection point or point of inflection, but just for the notes, right? That's what it's going to mean. So we would say G has a point of inflection and changes from concave up to concave down, right? Concave up, concave down. Concave up to concave down, because I don't want to write it all out. Okay, so if we know that's true about our original function, right? It has a point of inflection, changes from concave up to concave down. We can jump to our second derivative pretty easily, right? That means our second derivative had to have equaled 0. and it had to change. Concave up means your second derivative was positive. Concave down means your second derivative is negative. So if it changes from positive to negative, that's good. Now let's talk about what that means for our first derivative, because this one's a little less intuitive. So if your second derivative equals 0 at that point and then changes from positive to negative, well, if my second derivative is positive originally, that means that your first derivative changes from increasing, because your second derivative was positive, to decreasing, because your second derivative turned negative. And we can kind of think about that on the graph as well. So we did have slopes that were increasing. So I had 0, and then I had 1, and then I had 2, and then I had like 3. And then at my point of inflection, all of a sudden they started going back down again. So I was at 3 again, and then 2, and then 1, and then 0. So my derivatives, my slopes of my tangent lines went from increasing to decreasing. They're all still positive, in this scenario, but they were going up, they were getting larger, my slopes were getting steeper, and then all of a sudden my slopes weren't getting steeper anymore. So that is why that's why it makes sense, right? If your second derivative is 0 and changes from positive to negative, that means that your first derivative changed from increasing to decreasing at that point of inflection. All right, let's go ahead and talk about this next one. So for this point, we still have, I would still say that G has a point of inflection or an inflection point. But this time we're changing from concave down to concave up. So that's just going to change some signs and pieces down here, which means that my second derivative still equaled 0 at that inflection point, but it changed from negative to positive, which means that my first derivative changes from decreasing to increasing. Cool. All right, let's go ahead and we'll look at this last one. So on this graph, this is basically, how do I do this? So we have a graph, so this is a point of inflection where your graph changes from concave down to concave up. So you can say that all the same info for part D, right? Because here I still have a point of inflection where my graph changed from concave down to concave up. So all of this stuff still applies to this piece of information here. I don't want to take away from that fact, but I do want to talk specifically about the fact that this is a saddle point. And then the same thing will go for F. So F changes from concave up to concave down, has a point of inflection. So I would still say that the same info from letter C applies here. But again, my focus wants to be on the fact that these are saddle points, whereas these weren't previously. Remember that for saddle points, our original function, so let's write down our original function. So F, we haven't dealt with the graph F yet. G has a saddle point. How do I spell saddle correctly? There you go. Which means that my first derivative equals 0, and in this case, in this scenario, my first derivative before this value was positive, and then afterwards it's still positive. So I still had slopes that were positive before and after this saddle point. So you would just say that your graph on a sign chart, it would change from positive to positive. For letter F, your G has a saddle point, which means your first derivative was equal to 0, but then at that point, it changed from negative to negative. So this plus the same information from part C would be all the information you could tell about this inflection point / this saddle point. Same thing for letter E, had the same information as part D plus its saddle point information.